we're going to go over how to do some problems again. After today, tonight and moving forward, I expect that you get into lesson 23, which is digital, and kinetics 2 hard. Like, get into it. Yeah.
There's like a lesson 24 on like the schedule. Are you getting that out like later? There's a lesson 24.
Right, but yeah, it says when I hand it out though. On the third column. The third column tells you when I hand stuff out. Oh, now we know how to think. Okay, here we go. I want to talk about number 3. So, if you can get that, please, out, that'd be awesome. Number 3 on integrated rate law practice 2. All right, so I hope first that this would make sense. Let's read this for a second. It says, an isotope has a half-life of 63 years. If there's a 100-gram sample of it, how much of it will remain after 3 centuries? I don't know if this makes sense to you, but all this is just notes. So I want you to just make sure that you're using them as such. Is that a half-life, in general, works in a really simplistic way, but students will mess this up. If I start there at 100 grams, so a lot of people can label this as this is a half-life, this is a half-life, and so on and so forth. It's the same idea of what I'm doing right now. How much do I have? So I'm starting at 100. How much do I have after 63 years? 50. Okay. And this is where students then will make a mistake. Now, me drawing this out usually stops them from doing that. But if this was just on a test, the next answer, when I say, well, after 126 years, a lot of people will say 0. And I think you can at least see why you make that mistake and go, oh, well, it took off half the first time, so the other half will disappear after 63 years. That's not how half-lives work. How much is left after another 63? 5. Now, and if you're like, no, I would never do that. Right, because I have this up, but if you're going too fast, it's really easy to do. I'll just say that. So then here, this would be 12 and a half, correct? Right. And then what would be the last one? Yeah. And so on and so forth. I mean, it's going to get smaller and smaller and smaller, but the same amount of time, you're not getting rid of the same amount. Just like we talked about in the beginning, kinetics. The beginning, the initial rate is always the fastest. Now there's not as much, so you're going to lose less and less and less. But the problem is in an issue like number 3, this doesn't come out clean. It's not like this divides into it perfectly. So it seems a little cumbersome the first time, but this will help a lot on a problem that's on the first page, the first couple problems on kinetics 2. So please write this down. Amount. You guys, if you do not have your own graphing calculator, please grab one that's not labeled. So amount remaining, what we do is so this looks a little cumbersome, but it works really nicely. And you don't have to do any kind of weird derivative or determination of something else. And the first, just looking at it doesn't make a lot of sense, but once I write it out, it will. By the way, what I'm doing in a couple minutes, I'm going to hand out some tape. And what you've already noticed probably is that people put their names on the sides of these calculators. These have to stay in here. There are 4 that are in the SRC though. So there aren't a ton of problems that you're going to need these. If you feel like, well, yeah, but that's all we're doing right now. Right, because I'm trying to submerge you into how to graph this. A lot of them are already going to give you orders, but if you need to be able to do it on your test, when we do have it, you will be required to do one problem, like an integrated 1, 2, or 3 practice problem. That's why I have given you so many examples, and we'll have a couple more as we get closer to the test. But what I'm just trying to say is you don't need it every single day, you don't need it every single evening, but if you do need a problem, like, oh shoot, I need it for that, you can come and do it. But while we're doing anything in class, you have a calculator that is yours, so you can't be like, well, it wasn't set up right. You set it up, so yeah, it is. Okay, so how this works, simply put, you have the initial amount, so I'm starting with 100 grams. And now, I put a 2, and here's where you just have to make sure, like everything in chemistry, units match. So half-life is 63 years, so what is the time I'm dealing with right now? How much, what am I concerned with? How much is remaining after? 3 centuries, but I'm gonna write probably 300 years. I could write 0.63 centuries, but it's kind of a unit I don't really want to start getting into. So I'm gonna write 300 over 63. So a century is 100 years, so 3 centuries would be 300 years. Okay. My suggestion to you, you can do this any way you want. I would take 300 divided by 63, and then, you know what, I'm not going to assume anything right now. In case, I've always found students, even with their normal calculators, you never do this. So I do 300 over 63, and I get an answer. What I do is 2 caret. Caret is the little triangle. It's above your division. And then what I do, in case you've never done this before, second in answer, it's to the left of your enter. If you've never used answer, then today is a mind blow for you. If you'd use answer, good for you. But if you've never used answer on your calculator, on any calculator they have now, you're rewriting stuff or memorizing things that you don't need to. It takes the most previous answer, and then I would take 100 divided by answer. And if you do all that, I need you to be able to get this answer. I got this. And what is my unit? Grams. I want to make sure you're understanding what you're answering, not years. How much will be remaining? 3.68 or 9 years. What? That's how many grams will be left. Now, it's not mind blowing, but I think it's kind of cool to be able to apply something like what? Oh, sorry. To say like I have a certain amount and I know a half-life, and I can say whatever timeline there is, I can predict how much is left. That's part of kinetics. I can predict how much, how fast, all that stuff. So I would have 3.69 grams left. If you can't get that, I will definitely go over that with you eventually. Okay, so that's how you apply that problem. So let's move on to integrated rate law 3, and if you've already done it, that's great. I'm going to go over it though again. I want to make sure that we are on the same page with all of this. Really important. So, if you've not done this, even if you have, you know what? I want you to do it one more time. So some of you, if you've been on the point and really doing it while you've been being asked across them, please, what I suggest doing right now though is go second in the plus sign and hit, I think it's 4. Anybody, is it clear list is 4? It's important to clear lists, otherwise it just gets in the way. The reason why I say that, I'm not trying to stop you from cheating. What happens is, what if you have a list that's longer than the one you have now? It's a pain. So if you just clear list, believe me, it doesn't screw up your L3 and L4. I wish it were like an Excel spreadsheet where once you punch it in, it would just calculate it for you. You have to reassign your L3 and your L4. Okay? So this is what I'd like you to do. I'd like you to try to just get to the rate law. What is that? Let me give you a head start. Here's the whole point. In this case, it is A. I need to know the rate order, the order of the reactant. Again, if you've done this, let's just do it one more time to make sure out of a weekend that we understand this. So you need to plug these things in. If you're not sure where to go in the beginning, I will help you with that. You go to Stat, you go to Edit, and then this should pop up, right? All right, start getting your data in there. Please don't forget L3 and L4. Someone tried to graph without L3 and L4. Yeah, were you not here on Friday? I can't remember. It was on the cart, so maybe.
I don't know why.
Okay.
Thank you.
Yep, definitely. If you have questions, it's time to ask. Like, yeah, honey? You doing second and then memory? Second and plus sign? Plus and then 4. And then the end. We don't want to mix them up, so, and then, we need an unknown one. What do you mean?
Like there's
We're missing some?
yeah, more like the like
Mix them up. Get as many as you can. what, here, let me just give you a Post-it note, and then, or here. I need this, so. You have other two? What I would suggest, here, just put it on the front, just which ones you're missing on there.
Okay.
I wanna make sure that it's the same way. I'm gonna come around, if you're borrowing a calculator, again, please make it like this. You put it on the cover on the side, so then it's easily seen. And put it on, with something that's not going to smear or anything like that. And then you need a graph, so what are you doing then? You should have already set up your plots when you came in. You hit, you turn one of them on, right? And then you hit graph zoom 9. And then see if it's straight or if it's. No, sorry. An extra beaker for each class needs to be all the unknowns. I believe there's 14, so it should be U1 to 14. I thought mine was still in there like that, but I could be totally wrong. Hey Chris, are you able to make a line instead of just dots on yours too? The reason why it's important to set lines, guys, not just dots, is that there's a couple times where you'll actually have it look kind of like a straight line, and if you have it actually lined instead of just dotted, it'll jump out. Again, we are putting the tape like this, Morgan, on the side, just so then you can see it right away. And more. So on the cover, on the side. Okay, if we're there or not, that's about the amount of time it should have taken, to be totally frank. And if not, we need to continue practice. What order did we find? First or second? Second, okay. So, if you're still having problems, please come in. It'll take probably 5 minutes with me, and you'll be fine. But, let me explain something. On the actual test, AP exam, you are not required to have a graph calculator. So this is not actually something you can be doing in May, but it's really important for you to be able to do. This is something that most AP teachers will require their students to be able to do. But, let me explain. So you don't get the graphic. Let's say somehow they gave you data, or they told you already that it's second order, okay? So this is, by the way, the rate law. But then on the side it says this. This is why on the integrated rate law 2, how important it was that I had those 3 graphs. Without looking at your graph, what would this graph look like? You should know what these look like, a generic drawing. So a lot of you would go, oh, I know, it's like that, because it's second order, so it would have a positive slope. Why is that wrong? Okay, I'm going to keep trying to point this out. I'm not trying to trick you, it's just how it works. They'll have different labels of your y-axis. So you need to understand, oh, wait, so it's first, so you do that. Why is that still wrong for this problem? Because it's not a first order, right? So, which one is it, green or red? Okay, so if you look back at if you're like, whoa, what? If you look back at integrated rate law 2, we have 3 graphs. You need to continue to understand that 0 in first order will have a negative slope. If it's not that order, it will be curved. If it is that order, it'll be straight. Second order, because, and I think it's actually not a horrible leap to understand it, second order is inverted, right? It's 1 over. That's why it flips the script. It flips the rate, the slope. So that's why it would be a positive. So if it weren't second order, and it had this on the side, but it wasn't second order, then it would look like that. But it was second order, so your graph should look like that for the second order one. But that's not what I'm asking on that part. All right, let's continue. So I would write that on the side if you didn't already. Like, what if that was the graph? Let me discuss some other things. I'm trying to throw a little different flavor into each of these problems to give you a better idea. Let me just be very blunt. Integrated 1, 2, or 3 is in a direct kind of example that I will be asking on the test. Things like that. So those kinds of follow-up questions. Can you do that on the test? So determine the integrated rate law. The integrated rate law is simply the y equals mx plus b. I've been very upfront about this. You have an orange sheet. There are 2 of them on the orange sheet. That is what you get in May, so that's what you get every single test. So, what do I need to do? I need to make sure I'm writing it to the integrated rate law. Now, if you want to copy it directly off of the orange sheet, that's fine. That's not the way I remember it. I remember it a little differently. Very important, you always put the compound in your brackets. So in this case, it actually ends up being A, but if it was like H2O2, you put H2O2. So that is literally the integrated rate law. That's it. What would it be for zero order? And this would be for first. Sorry if I'm in the way. I'll move in a second. Right? Like what's the difference? I told you from the beginning, the one brute force memory that you're going to have to come down with, which I'm hoping that it's already starting to happen, zero order is concentration, first order is natural log, second order is inverse. That's it. If you can apply those ideas, everything else comes in play. Why are these two negative and that one's not? It has a negative slope, so we have to counteract that. This one gets flipped, so there's no negative. If you forgot that, two things. One, it's on the orange sheet. This one and this one are on the orange sheets. Secondly, though, as you plug it in, it wouldn't work. Like you would have, it's not going to work. Like if you forgot the negative, it actually will give you an error with a natural log. I'm almost positive. So just know that. Okay, so now you're back in the game. You have to do this for me. It says, find the rate constant. I'm going to be quiet for a second, and then if you're really struggling, I will show you. But it's on this screen. I'll tell you that. It's one of those screens. Let your calculator do it, though. Your calculator needs to find the rate constant. So try it out. Today's the last day I'm focusing on this. You will still need these from time to time, but we are going to move into all the other ways we can use the integrated rate laws without having to always graph, and just all the different situations. And we have to learn just a couple other bigger ideas as well. So. If you have an error, there could be an issue.
Whenever I graph it,
Well, then that means your plots are wrong. So what do you need to do? Unless if you have a TI-84 plus, it will say line rig, you hit enter. So if you're like, I didn't even know how to do that. You hit stat, calc, I just hit the 4 button, I don't scroll down. And it goes to line rig. It doesn't tell you, unless if you have an 84 plus, to do anything else. You need to physically put in the plot that you want. So in this case, we want L1, so you do L1, it's second in the 1 button. You do the comma that's above the 7, and then L, in this case, what? What did I want for this one? L4, because it's a second order, right? So I want an L4. Really important. And what is it, like 11.98 or something? 11.96?
yeah.
Okay, what's the unit? Let's talk about that quickly again. So this is how this works. Best way I can do this. If I have this sitting right here, this is what I have. This is moles over liters, in this case it's seconds. I have something here, and then this is molarity over liters, which is both squared right now. So, think of it this way. This times this equals that, right? So, I need time there. And then in this case, what do I need to get rid of? I need to get rid of one of these, right? Because there's only one of these. That's why I need liters over moles here. If you watch that video of that guy who has the calculator image and he's doing all this, which you haven't, and you're having struggles with this, I would watch it. This is how he does it. And I do it a little differently, but it's all about the overall order. So right now it's a second order, so it's one less. So what he does is he just puts an M times the time. This is always inverted. So this is moles over liters, this is liters over moles, so I have to flip this. So he always does one less than the order. So it's -1. Just as an example, if it were 7th order, then I do one less than the order. What I like to do is this. I remember, oh, I need to get rid of liters and moles. So I automatically do this times the time. This is my generic way of writing it. And then I always put the number that's one less than the order. So if it were, again, 4th order, I put a 3. Now, why not a negative? Because I've already flipped them. If it were 2nd order, that's why it's a 1 now. If it was 1st order, it's actually why these are both gone. Now that's why it's over time, because it would be a 0. So it's, for me, it's always liters over moles times time, and then it's the exponent is 1 less than the overall order for the liters and the moles only, because I have to get rid of them. So this is 2nd order, so that's why these are 1s. So that is my rate constant. All right, we have 2 more to go, and we're really close on time here. Determine the half-life. Okay, on your orange sheets, and I'm sorry because I did not copy the last one, so I thought we were all done. There is a half-life for 1st order, but not for 2nd. Now you can memorize 2nd, or you can do it this way. You just take half. Help me out. Is it 0.01, the original? Is that right? I'm sorry, 0.01? What? Last hour told me 0.01. Seriously, what the heck? Okay, that's awesome. Maybe I'm wrong. I don't remember that one. So I just take half of the original amount. So then, I don't know how you would do this, but I would actually calculate the left first, and then I subtract that 1 over that amount, and then I would divide. So I would take 1 over. Oops. I know we're almost at time. I need you to just to stay for one last quick thing. Fine. Now, here's the thing. And I know I'm rushing a little bit here, but you need to understand that half of this would be 0.5. Maybe they did tell me that. So the thing is, that's more than this. So it's got to fall in here. But let's just say 0.5 was way down here. Then it needs to be between 15 and 20 seconds. Like, let your answer or your table actually help you out. This looks like a really fast reaction. The rate constant's really big. It's fast. Like after 5 seconds, it's 90% of the time it's gone. So I got this. Now, tell me if you didn't. Is that what you got? So in less than a second, half of it's gone. Well, the data table actually kind of tells you that that's true. The last question, help me out, what percentage does that say? Because I cut it off. Sorry, everyone said it at once. I just want to help you start this off. What do I have to think about, though? I need 22.8. So all you need to do, it's the exact same concept. Instead of this, now I need 0.228 of my original amount. And then in this case, it's not a half-life anymore. It's just time. So I hope you see the similarities. Once you're dealing and talking about time, all you need to do is plug it into an integrated rate law, and you can figure it out. Okay? So the left side's always how much you're talking about at that amount of time. The right side's the initial amount. Okay? Get into kinetics 2. Get into lesson 23, because I'm going to start answering questions. If you did not try it first, I promise it will not have as great of an effect. Please shut down your calculators. Have them labeled and return them. They will be available for you. I have 4 of them in the resource room, though. So you don't need to come in here necessarily to grab your one. So continue to work, and we will see you tomorrow. It was sent to you, yes, in an email.